Well, good afternoon, everybody. I'm going to talk about a real passion of mine, which is actually making powder. Started when I was 18, working for John Courtney, and just want to talk about the importance of a good grind and good powder today. Just before I move on, we're working with Price Plastics in Australia, in the eastern states, and they're distributing our specialty materials, so sort of did put this presentation together with them. And just talking about what actually makes a good powder, but also there are other contributing factors in your moulding process. So material selection is one of them. The density and MFI are controlled by the polymer manufacturer. So, for instance, you can get a 3 MFI, 6 MFI, they're going to mould completely differently. So it's really important to start with the right base resin in the beginning, and your powder supplier can help you with that selection. Mould design, that's another important part of the process. Optimal mould design will take into consideration the powder flow, correct tolerances around tight areas, kiss-offs, radiuses in the corners, and as well as having adequate free volume to allow the powder to flow around the mould. Processing parameters. The way the powder flows in the mould influences the moulding parameters. So the RPM, rock and roll machines, oven temperature, all play an important role. And then finally the powder. A consistent dry flow, bulk density and particle size distribution will help you make a repeatable product. So, just talking about the 3 stages. So, we have here, this is what goes into the extruder. Now, sometimes people refer compounding to extrusion, pretty much the same thing. But before we actually compound the material, we use a master batch, which is a concentrate of pigments and other additives. And that master batch is in a carrier. And a carrier could be the same resin that is going to be compounded into, or it's a carrier that's a material that's very good for dispersing the pigments and additives that you want to put in. Now sometimes the resin can be more than just one resin, it can be several. And for instance, our bio-TPCL is a polyester and a polyethylene, and that's what you call a polymer alloy. It's a blend of different materials. And the other thing is, this stage here is a very important stage at pre-mixing prior to compounding to get the right amount of additives that are going into the extruder. And this, you'll see a presentation later on today about robotics, and you'll see a flame retardant product being moulded, and that has a lot of different additives, and it's very important to get good UV and compound in the flame retardant properties. So this, after it's compounded, it comes out in a granule, about 4 or 5 millimetre, and then it goes into a powder which is delivered to you. So, extrusion or compounding. This is a picture of one of our lines. So materials are blended before the feed goes into the extruder. The extruder melts the polymer and the master batch. It is then mixed to form a compound which is pelletized into a granule. The granule is then sent to a grinding machine and it's processed into powder. You can see this machine here is doing black. So to talk a bit more about an extrusion line. So this area here is the feed section or the hopper, and above that you would normally have a mixing station. And the material goes into the extruder and travels along the extruder, and you'll see as you can see the screw here is actually, the diameter is a lot smaller here compared to here, and this is where the granule is starting to melt and being transitioned through, and you get to this stage here and it's compressed. So it's travelling up the barrel and compressing the material, and it's also mixing, helping to mix the product. And sometimes the material actually goes over the flights, and this also helps with the mixing process. So at the end here you have a breaker plate, and the breaker plate is there to create some back pressure, and the back pressure also helps with the mixing. In that breaker plate, you can have screen packs as well, and the screen packs actually also contribute to the mixing. Some extruders on the screw there, they have mixing heads, which is what we do. That also helps with the mixing process. So after the breaker plate, it goes through an adapter to the head of the extruder, and there's two ways you can make pellets. One is they use water, a die face cutter, and the pellets basically come out of little holes. The plastic comes out of little holes, and there's a blade that chops those pellets, and it's cooled instantly because it's using water to cool it. Those pellets are transferred, and they're dried, and the water is separated, and then it goes to the grinder. And then the other way, they have strands coming out of the extrusion die. They drag the strands through water into another pelletizing unit. So over here is the actual photograph of an extruder. You've got different zones, and these zones are used for heating and cooling. So there'll be a heating element there on each one of these, and a cooling unit. So each one of those zones, depending on what you're doing, will be set at different temperatures. And the most important part of the extrusion process is the melt temperature. And the melt temperature is measuring the actual temperature of the resin. And what we don't want to do is we don't want to process that material too hot, because it starts taking out all the additives, for instance the antioxidants, that are then used in your process to protect the product during the processing. So very important to make sure you don't go too high in the melt temperature. So the importance of mixing during the extrusion process. So we use a computer-controlled dosing unit, and this part of the process, as I said before, is very important. Every 10 seconds, that dosing unit sends a message back to our computer system to tell us how the additives are being added into the extruder and what percentage has been added. And then during that, once the material has been mixed and it goes into the throat, the materials are dispersed through the compounding through the extrusion line. Master batch is used in the compounding stage as the pigments are already pre-dispersed in the master batch. The mixing quality and colour and contamination is checked throughout the run. So, got some examples here of plates, and this is orange, obviously, and grey, and the orange is well dispersed material, and the grey is not so well dispersed. I'll pass these around, but this is actually a melt out of powder, and what we do is we also do a press out straight after the compounding line when we first start, and this is a sample from Price Plastics. But once the machine is started, we actually check the powder, and we do a melt out of the powder because it also highlights other issues like orange peel, and it does show up dispersion and incorrect mixing a lot more accurately. So I'll pass these two around. And you can have a look at what I mean by picking up certain aspects. This is an example of Price Plastics has mixed some natural powder in with the compound, and these are two methods of checking the contamination, but in the press out you don't see it so much, but in the actual powder melt out you do. So if you put it up to light you can see the difference. So the milling. The granules from the extruder are fed into the mill, and rotating plates share the granule into small particles. Now, when you talk about rotating plates, there's not two rotating plates. It's just one plate and one station, or two plates, but one is stationary, and the other one is moving at about 4,000 revs per minute. The plastic particles are continually milled until they pass through the screen system, and all the oversized particles go back through the mill to get ground down if they don't pass through the screening. The process generates a lot of frictional heat, and it's done very close to the melting temperature of the resin. So I just got an example here of, we just made up a little example of the sieve, or one of the sieves, and what you have is the mesh on the top and some mesh on the bottom to hold the balls in place, and these balls, as the sieve's rotating, helps to get the powder flow through the screen or the mesh. So you might have several layers of screens in one mill setup. So here we've got an example of a grinding machine. And you can see that's the granule being in the bin, being conveyed up to a conveying system and then dropped into a hopper, going into the grinding chamber. And this here is oversized particles coming back from the sieving section into the mill. And then air is used to convey the powder up into the cyclone. And the cyclone separates basically the powder from the air. The powder drops down into the rotary gate, which is sealed, so that no air can pass through and suck the powder back up through the screening system. And then you've got the powder, and it's actually going round through the different screens until it either goes through the screens into bagging, or it goes back out to be reground. So the operation of the mill plays a really important part in the quality of the powder. So what is happening during grinding? Our mills are attrition mills, and they're grinding at ambient temperature. Now, you've probably sometimes heard about cryogenic grinding, or hammer mills, or even air mill. Cryogenic grinding, for instance, will take a whole system and it's frozen basically, and it's frozen so that it can grind hard to grind or difficult to process materials such as polypropylene and nylon. So during the grinding process, the particles actually develop some tails. And we actually grind at really high temperatures, as I said before, very close to the melting temperature, so that we can actually polish the particles and take those tails off. So we need to actually classify the material coming from the mill to remove all the larger particles, which, as I said, gets reground. The dry flow indicates that we have successfully polished those particles, and so does the bulk density, also shows that the particles are polished well. Particle size distribution is an indication of the correct gap setting, as well as the screens are correctly fitted. But it's also, when we're grinding powder, we're not just grinding and everything's not ground just to 500 or 600 micron. There is actually a distribution of particle size, and it's that correct distribution that gives you a nice surface finish, the correct fusing of the materials, and also helps with the dry flow properties. So this is an example of a magnified example of powder particles from Roy Crawford's book, and you can see tails on the low temperature material, and on the higher temperature ground material you can see not so many tails, not like ball bearings, but you know, it's a lot. This material is going to flow a lot better than this material. So, looking at the dry flow is a measure of how the powder will flow in the mould before the melt phase. The key factor in the dry flow is the particle shape. This will allow the powder to go into tight areas, threads and other hard to access parts in the mould. Some people confuse dry flow with melt flow. Dry flow is a factor of the material before it melts. Melt flow is a measure of the viscosity of the material when it is melting. So I've got a picture here of the dry flow funnel. See the powder, yellow powder going through the funnel. And this is the melt flow index tester. So I mentioned before about high and low melt flows. This is the instrument that measures that. So this here is a unit that heats up the material, and granular powder is put into a rod or a tube there, and this is a weight on top. And as the material has been heated, the weight forces the material through the die, and you'll get a strand of polymer coming out. Now that polymer there is then weighed. So if you have a low melt flow material, not so much comes out of the extrudate, or doesn't come out as much as a higher melt flow material. And that's how you get the measurements, by the weight of the material that comes out. So a high melt flow material will mean more material coming through that die. Poor particle shapes and poor dry flow will lead to bridging across narrow sections, slower cook times, which I'll show you in a minute, voids in the finished skins affecting impact strength, uneven wall thickness, and poor surface finish. So this is an actual test of the dry flow test being conducted. And we're just holding the powder in the funnel, let it go. In this case, just using a phone to measure the amount of seconds it takes for the powder to flow through. We actually put 100 grams of powder in the funnel. And this is another test, which I'll talk about in a minute. The powder goes into the cup, and that cup measures the bulk density. And that's measuring how well it will pack, the powder will pack down. So the dry flow for that particular powder was about 27 seconds. So we're just skimming off the top there of the bulk density cup, and that will be weighed. And basically the weight of the powder determines the bulk density. So the bulk density measures the way the powder, this ground powder was packed together. If the tails are present, the bulk density will be lower. You may have noticed when you're moulding that sometimes you can get more powder into the mould. It seems like the powder is taking up more area in the mould than what it should. This is relating to the bulk density. Bulk density is checked on a regular basis through the manufacturing of the powder processing. And bulk density is measured in grams per cc or grams per litre. A powder will often have a bulk density of 0.35 to 0.37. So during the grinding process, we can't get the powder to be exactly the same bulk density all the time. There will be some variations due to the process, but we've got to keep it within a tight limit. When bulk density is too low, the volume of powder in the mould can prevent the powder from flowing. I'll give you an example of that in a minute. And if the bulk density is correct, it actually helps with the heat transfer into the material. So here's two materials, both 6 melt flow and 932 density. And on this side is the material that has good flow and a good bulk density. On this side, bulk density is not so good, and the weight of the powder is exactly the same. So you can see between the two of them, there's a difference. And I'm sure some of you have seen this in the moulding process. So particle size distribution. The particle size will have an impact on dry flow and bulk density, but it doesn't influence the dry flow, doesn't influence the flow as much as the particle shape. There is no agreed particle size distribution for rotational moulding, but if you look at Roy Crawford's book, he talks about 500 micron grind. We have customers that we've done 400 micron grind, 500, even up to 1,000 micron, depending on what the end application is. So David's talked about today about too many fines and how that can be a contribution to the possibility of dust explosion. So we certainly don't want a lot of fines in our powder, and we don't want a lot of courses coarse material. So we've got to find that right balance. So the particle size is controlled by a few factors. Plate design, by the change in your teeth you can change the particle size distribution, the gap and the screens. And also, if you don't maintain your mills and you're not changing your plates on a regular basis, a blunt set of plates can give you more fines. So, the testing the particle size distribution. The PSD, as some people refer it to, is tested to ASTM test method 1921. And this is checked by placing 100 grams into a stack of sieves like that. And these sieves are shaken for 10 minutes, and each sieve represents a different particle size or mesh size. And as you can see here, you've got several different sieves, and then you have a pan at the bottom, and we measure what is retained in that pan, because this powder and probably the next screen up are the ones that can contribute to issues in the moulding process, and we don't want a lot of those fines in there for reasons we just talked about. So the results during the process are recorded and compared to specification, and if we see any issues we can adjust either the screens or the gap or whatever we need to do to get back on spec. So these are examples of what happens when you have an acceptable dry flow and bulk density and not so good. So this mould here is quite difficult to get all the powder into the mould, and you can see what happens if there's not a lot of space for the material to flow around or the powder doesn't have good flow, we just don't get into that area. So again, these are basically the two different materials I showed you. You can see that here there's no material, here there is. And if you have a good look, you'll be able to see in the different areas of this test mould that we use in our R&D to check the powder quality and melt flows and how materials flow. You'll see the different areas. Now, that's exactly the same material, but ground differently. This is material ground well, but with a 3 melt flow. And you can see that the 3 melt flow has done a better job because it's been ground properly, but it still doesn't quite get into the areas that we want it to. So in rotational moulding, again, selecting the right material is very important, and as we know, a 3 melt flow material in the tank market is a commonly used grade, but if for general purpose moulding, you probably want to use a 5 or a 6 melt because you get better flow, faster cycle time, better surface finish. So what we've got here, and I think this is the first time this has been done, is we've got a little moulding machine, and we're going to show you what happens during the moulding process with good powder there and bad powder. And you can see already that this powder's taken up more area than this powder, even though it's the same amount of material and weight. So here you can see the powder's tumbling. You can see this isn't tumbling that well, whereas this is a lot smoother. And the materials are starting to stick to the wall. Again, the good flowing powder is actually starting to build up a little bit quicker. And here you can see the same time, the bubble dissipation for the good powder is the bubbles are leaving the material a lot quicker than the poorly ground powder. And closer towards the end of the cycle, you can still see the difference. The inside surface here is a little bit more rougher, and getting really close to the end now, there's still some residence of not flowing or the material not melting out. And again, these are the same melt flows, same densities, same batch of raw material. And now the powder is it's all solid and it's cooled down. So what we did also is we just thought we'd throw in some micro pellets, and again you can see here the poorly ground powder, good powder, micro pellets, all the same weight. Micro pellets take up a lot less volume. Just to show you the flow, again the micro pellets flow very well. That's good and bad. Micro pellets, as I mentioned before, the powder, you have a distribution of particle shape and size. Micro pellets are generally all one shape, so surface finish with micro pellets might not be as good, and the dry flow properties of micro pellets are more like 10 or 15 seconds compared to 27 or 25. So they're going to flow around the mould a hell of a lot quicker than powder, and so if you're going to use micro pellets, you need to alter your moulding cycles. So, tools that you can use to test the powder. I mean, you heard before about people testing powder. I was just speaking to a moulder today who tested some powders and compared the different properties. And we recommend that it's a good idea to have your own dry flow funnel. They're not expensive. Armour actually supply them. And magnifying tool, just a little glass, one of these. That's all you need you can compare the particle shapes and see if there's any tails on any powder that you might be having some issues with. A stopwatch or iPhone or any type of phone to measure the timing, and a small scale. And you can actually have a sieve if you want to check to see if you've got any oversized particles. And we're going to have the dry flow funnel and everything outside later at morning tea, so that you could actually do some testing if you wanted to. So, now what happens if you do have some problems? Well, the first thing is, if you've got some moulding problems and you think it's related to the powder, review your production parameters. You know, the question is, one of the things is the correct material being used? And as I explained, you'll see in the samples, you know, you can have some natural material and you'll be moulding a 5 melt flow, and then your operator throws in a 3 melt flow, and it's going to mould completely differently. And have you changed anything? I mean, 90% of the time, customers do ring us and say, well, look, we've got a problem with your powder, but 90% of the time, it's actually some other factors. And one of them is quite common one is blocked breather tubes. When you get blowholes in the parting lines, you can have issues, and it's not a powder-related problem. Mould release, David's talked about, over application of mould release can affect the surface finish. And also, we've seen areas where, for instance, making kayaks, the mould has preheated a certain area to get more material into that area, but he's put too much heat in, and so the powder hits it melts straight away, but doesn't have enough time to actually fuse out and melt out, so that there's and it creates voids in that area. And obviously, if the correct program's been used, if the mould been put onto another machine or placed on the machine differently, will all affect the way the material is going to flow in the mould. So if you have had a look at everything, and you still have a problem, you do need to contact your supplier. A really good way of letting us know what's going on is to send us a photo, and it's really easy. Just on your phone, take a photo, send it by text or by email, and always tell us, obviously, the grade and the colour. Batch number is really important, but the bag number is even more important, because in a run of material, we can do a 1 tonne run or we can do a 50 tonne run. So where in that 50 tonne run is the issue. So the bag number is really important, and what is really good is if you can take a sample of like half a kilo or a kilo of the material close to the actual issue and send it to us or to your supplier, and we can check that powder and find out what's going on. So just that's about the end of my presentation. And just wanted to show you the references for the presentation. Roy Crawford's books are really good, really practical, a lot of information in there, and you can actually get those through Armour as well. Thank you. Should have asked if there's any questions. I'm happy to answer them.